Okay, so let's get started with lecture 2. And so last class we started discussing how to formalize computing, and to that end we started asking the basic question, how do you even represent things, right? And we started talking about representing objects and how powerful a specific representation can be compared to other representations, right? And also we were kind of addressing this idea of composing representations. Okay, and today we will see how we can represent everything via composition. And as I said, it's always fun to think or kind of unpeel what lies beneath and imagine that everything you see, even the screen, is really just one string of zeros and ones, right? The way it's stored is a single string of zeros and ones. We'll see it in a kind of a toy example in action as well. And then once we know how to represent stuff, we'll talk about computing functions. Not defining what computing is yet, but what our goal is. Okay? And then we'll start talking about simple operations. Okay, that's the plan for today. Right? And let's recap where we were last time. So there was one important notion that we introduced last time, which was prefix-free encoding. Since I'm here, I can do this. There we go. Right, so we discussed the notion of prefix-free encoding. These are encodings. In particular, any two objects will be mapped to different strings, but also they have to be mapped to strings which cannot be prefixes of the other. Okay? And then we saw how, why prefix-free encodings are useful for us. Okay? Any questions about either the definition or the statement of the theorem? The point is that if you have a prefix-free encoding, it's easy to compose these encodings. So if I can represent numbers in a prefix-free way, then I can represent lists of numbers. Okay? All right? Now, the next nice thing would be to be able to do this without having to design the prefix-free encoding from scratch. Right? So for instance, we said, okay, we built an encoding for rational numbers by getting a prefix-free encoding of integers. Right? So we said, Q2 binary, which takes rational numbers, outputs binary strings, was you take a rational number, p comma q, the numerator is p, denominator is q, and you just encode it as prefix-free encoding of integers encoding of the numerator concatenated with the encoding of the denominator. Okay. So now we can represent things like 1/5, 2/17, whatever else you want. Okay. Then the next question is, okay, what would be the next natural question? You tell me first. Any suggestions? What should we try and do next? Yeah?
Next, we try and build a list of
Yeah, so next question, natural thing is, okay, what if I want to encode things like 2/5, 1/10, 0.7, 0.6, maybe even -10, etc. Okay, I have a finite list of numbers like this. Rational numbers, we don't have to worry about arbitrary precision. How can I encode this? Okay. So, I mean, you can imagine why this would be very useful, right? We already have encoding for rational numbers, but now I have to encode a list of rational numbers, which is technically a list of lists of integers, right? So I can view it as okay. So how can I encode a list of rational numbers now? Any suggestions? Yeah.
So how we made numbers for hit it every bit and hit one specific length 2-bit that can only be seen in certain positions.
Right, exactly. Right? So there was something inherent in how we did the prefix-free encoding for integers, in that it wasn't very specific to the way we started out with. Right? We started with binary encoding of integers and then designed a scheme to make it prefix-free essentially. Right? Once we have prefix-free, we can concatenate things to get representation for lists of numbers. But this process, gives an encoding but doesn't give a prefix-free encoding. Right? So when we do this conversion, we get to encode more complicated things, but we lose the prefix freeness property. It's kind of inherent in the definition. Okay, we have to bring that property back. Okay. So that's what we're going to do. And say goal if okay, so let's say, actually I'm going to just write it as a claim. Given an encoding, okay, you give me some encoding, then I can build a new encoding P that is prefix free. Okay. And the idea, as was just mentioned, is to basically do what we did to get prefix free encoding for integers, right? So the algorithm you first compute the actual encoding. Now you duplicate each bit, and then you append 0, 1 to the end. Okay, so that's the whole algorithm. Exactly what we did for integers. It actually works for any encoding, right? So now, given these two tools, we can build as much, we can build encodings for as complicated objects as you want. Okay. For example, if we put these two things together, let me say ideas. What can we do? So for instance, I start with Z to B. Okay. So I'm just encoding numbers here. Then I convert it into prefix-free encoding. Okay, I'm still only encoding numbers. Okay. But now I can use composition to encode lists of integers to B. Okay. So this is lists of numbers. Okay. And list of numbers, for example, an image, as I said, is just a list of numbers, right? If you think of a text file, you can also encode it just as a list of numbers. You have ASCII characters. Each character has a number. It's just a list of numbers, right? So right now, we already found how to encode any text document as a single 0-1 sequence. In a proper way, you can go back and forth in a pretty efficient way too. Okay. So, let's say this is like, already at the level of encoding images, documents, etc. Can ask, okay, next, I can again do the same thing. Can do prefix-free encoding of lists of integers okay. And then I'm going to stop after this. I'm not going to do this again and again, but I can use this to composition to encode lists of integers to binary. Okay. Now it's like this. Okay. Yeah. So, once we do this composition, we lose the prefix-free property. So we have to get it back, right? So we use our disclaim, which converts any encoding to prefix-free. So you have to play these two things in tandem. I build prefix-free, then compose, then make it prefix-free, then compose, and so on. Okay. But at what level of abstraction are we? At lists of numbers. Sounds still somewhat made up category that you wouldn't really care about. But my claim is that it's really useful. Any examples you can think of? Yeah. I mean, matrices are already there. We already have lists of numbers, right? An LLM is just a long list of numbers. Yeah. Videos. Yeah. So you're at the level of encoding videos now, right? Because every video is just basically a frame. And every frame is just an image, right? So a video is just a list of images. Okay. And this is actually how stuff is stored. A video is stored on your hard drive. It's just one single sequence of zeros and ones. It's basically the same process that we're doing here. It's done slightly more efficiently, and you'll work with that in your exercise. Okay. So we are at the level of encoding videos. Let's say database of images. Digital library of books. Right? All of them, we've already found a way to encode them as a single 0-1 sequence. Okay? And if you do lists of lists, you'll get videos of videos maybe, and so on and so forth. Yeah?
Seems like very taxing on your resources.
Right.
Have people figured out things around that?
Yeah, definitely. In fact, that's the one that I just alluded to a second ago, that the only lossy aspect here is converting an encoding into a prefix-free encoding, right? So when we're doing this, we're kind of duplicating every bit. Maybe for small things it's okay, but using twice the memory that you would normally use is definitely something you wouldn't want to do, for large files, for example, right? So currently, this process that I mentioned here, duplicate each bit and append 0-1 to the n, kind of blows up the length of the encoding, right? So if, let's say, so the length of the prefix-free encoding is 2 times the actual length plus 2, okay, which is quite, wasteful. But in the homework, in the assignment, you will actually see how to do kind of, let's say, a more sophisticated prefix-free encoding, right? Which is plus okay. So instead of doubling the length, I'm only going to use logarithmically many additional bits. Super efficient already, right? And you can even do this again and get even better if you want, right? And this second process, this is what, as you'll see, is actually used in many representation things in applications. For example, if you're using any object-oriented programming language, for example, Java compiler uses this to encode new objects that you define, right? And so on and so forth. Okay? So this basic idea is already very powerful and allows us to represent everything pretty well. Okay, just as binary strings. Okay? And let's see if my code is still working. Okay, let's do this. Okay, let's see the code in action, what the ideas that we discussed in action with n to b. I'm only doing integers, natural numbers for now. So n to b is very simple. You're just encoding a natural number as binary. So for example, if I say 1936, if you want any other number, let's say 38. Okay, and if I ask it to decode, it gives me 1938. Very simple. Okay. Now, here's a prefix-free process which takes 2 function handles. It takes an encoding process and a decoding process and gives a new new function handles. One is prefix-free encoding, prefix-free decoding, and something which also checks if a string is a valid encoding. Okay? And I'm going to ask it to convert my encodings of natural numbers into prefix-free versions with the decoding algorithms. Okay, So as I'm encoding, I'm also maintaining the decoding algorithm, which is useful. I mean, it's not very important for the discussion that we've had so far, but you can easily imagine it being very important for applications, right? And maybe let's do, okay. We get some encoding. All right. Now this is representing lists. So it takes a prefix-free encoding process, decoding process, checker, and then implements a process to encode lists, to decode lists, and then that's it. Okay. You can see this long sequence is, whatever, 1901, let's say 1857, or tell me some other numbers, 2025. Yeah, okay. And if I ask it to decode, it should get back the original thing. I can ask it to do the same thing again. LOL. No. I usually get at least a few laughs for that. Okay, so now I'm encoding this list of lists, which is something, and this whole thing is just one long sequence. Okay, and ask it to decode, I get back the original thing. Again, I'm not cheating anywhere, right? So I'm giving the decoder this string, this long 0-1 sequence, and I'm getting back this nice list of lists. Okay, and the only thing that we did was just repeat this idea of converting encodings to prefix-free form, and then using concatenation. Okay, any questions about this? All right. Okay, so what's the takeaway from all of this? The one takeaway for us should be that when you're building a model of computing, right, we should not have to worry about the different modes of input. Okay, I mean, you want to build an application, you should be worried about it, right? But I'm building the basic hardware. I shouldn't worry about, okay, is my input going to be matrices? Is it going to be images? Is it going to be text? And so on. Okay. At the first level, you shouldn't have to worry about that. So for us, luckily, all of this representation stuff tells us we can assume without loss of generality that all inputs are binary strings. Yeah? Oh, sorry. Thanks. Yeah, I still haven't, I ordered a long extension cable for HDMI, but it's still not here. No? Okay. So we can assume without loss of generality that all inputs are just binary strings. Okay? So when you're designing chips or you're building the computer, we can assume this without loss of generality, because we know that there is this additional layer that we can do, which can convert anything into just a binary sequence. Yeah? Okay. All right. Any other questions about this? As I said, we're not going to open this box again. From now on, once we know for sure, there's no ifs and buts here, everything can be represented very easily as binary sequences, right? We already saw how to represent videos, for example, right? And we're not going to open this box again. From now on till the very end, maybe the last 4 lectures, we're going to assume everything is just binary sequences as input. Okay. Yeah.
Coding always just for 0, 1, and if it's
Yes. I mean, at least for the one that we did, right? If you do this slightly more involved thing, which saves you the factor of 2, then you have to correspondingly tweak it. Okay. All right. Any other questions? Yeah.
0, 1 is just like know when to stop, right?
Right. Yeah, exactly. It's like, we want like a tag which tells us that this is never going to occur anywhere else.
So does that
Yes, 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 definitely. You have to read it in sequences of 2 to skip kind of the duplicates until you find like a 0, 1, and then you stop. Yeah, exactly. Yeah. Yeah.
That's like this prefix tree way of encoding is like the smallest prefix tree.
You can actually do better. And people have figured out the exact limits of prefix-free encoding because it's such a fundamental thing, right? Prefix-free encodings are also very useful when you're transmitting messages, because you don't want to spend time saying, okay, I stopped sending. And what if that last thing doesn't come across? And then you're just waiting forever, right? So they're actually used, or at least, nowadays maybe they're not as important, but definitely in the early days, like for example, telegraphs definitely use prefix-free encodings and so on. Okay. Any other questions? Yeah. Oh, so p tilde is just like, I didn't define, I didn't build it here, but I'm saying there is a way to convert any encoding into a slightly more sophisticated prefix-free encoding where the length is better controlled. The one that we just saw is doubling the number of things, right? So if you do it 5 times, you're already at like 32 times the original thing, which is quite wasteful, right? So this is saying you can actually do much better. You don't have to multiply by 2 every time. You only have to add a few bits at the end every time. Okay? All right. And you'll do this in the homework. Okay? All right. So as I said, we can assume everything is representable as integers, as binary sequences, except something. And let me talk about that. Everything that we care about for computing can be, but there are some things which we cannot. Okay. And one of those very critical things that people realized a long time ago, almost more than a century ago, started with this question. Okay. So when we said we can encode rational numbers as binary sequences, but rational numbers aren't everything, right? We also have all kinds of other numbers. We have irrational numbers, we have transcendental numbers, whatnot, right? So we have square root 2, square root 3, pi, e, and everything else in between, right? We can ask, is there an encoding from real numbers to finite binary strings? Okay, yeah?
Depending, like, sequence of zeros and ones, like, because you just do BCDs, right? Is there like a limit on how many bits that the encoding is allowed to have?
It has to be finite.
Yeah.
It has to be finite. So for rational numbers, for example, if I just do, let's say, expansion, it might still be infinite. But we have found a way to encode it with finite binary strings, right? So for example, 1/3 is never going to stop, but nevertheless, we said there is a way to encode it. So that might not be the only way to encode. Now we are asking, okay, maybe for real numbers, if I just do expansion, I'm not finding a finite length, but maybe there's a cleverer way to do it. Or is there not? Okay. And what's the answer? Maybe you've seen it before. No, right? And this was, I think I find it amusing to go back or at least read about these stories from history of mathematics and even in computer science where things were, we take for granted, right? but were kind of astounding people at the time, right? And this is one of the best examples. So Cantor in 1876 showed that there is no one-to-one mapping from real numbers to finite binary strings. Okay, he showed that there is no way to encode real numbers as binary strings. Okay, so let me just take a poll. How many of you have seen this statement in one form or the other before? Okay, I see a few hands being raised. How many of you find it very surprising? See 3 people, okay? But I'm sure the answer to the next question is not going to be any hands, but let me ask you anyway. So when this result came out, when Cantor posted, people were aghast. They didn't believe him at all, even though he gave a full rigorous proof, right? For example, Kronecker, who was one of the most famous mathematicians at the time, called him a corrupter of youth. That was his review of the paper. That you're teaching blasphemy, you're teaching something which is not mathematics, that you cannot have 2 different sizes of infinity, basically. And Poincaré, another famous mathematician, did very important contributions across the board, said Cantor should be banished from mathematics once and for all. And Wittgenstein, a famous philosopher and logician, wrote, "This is utter nonsense, laughable, etc., etc." Okay. So, I mean, saying that basically things like encodings were a very contested topic. Okay. And eventually, I mean, Cantor at the time, I don't know how he survived these attacks, but he did. He still went on to do many other great things, although I don't think he was as well recognized during his lifetime. But eventually, people came around. For example, in 1925, almost, let's say, 50 years later, Hilbert said Cantor opened a paradise for us. Okay, because Cantor didn't just show that real numbers cannot be mapped. He also showed that there are other classes of objects that cannot be mapped to real numbers, and so on and so forth. Okay. All right, that's just kind of an interesting anecdote. But the summary for us is that everything that we care about, except real numbers, anything which is, let's say finite or even infinite, but countably infinite, can be represented as just binary strings. Okay? All right? So from now on, we're not going to worry about representing data. We always have a binary representation. And if you're building a computer, we just have to worry about manipulating bits. Okay? All right. So now we said at the beginning of last lecture that there's sort of 2 things, 2 important aspects to computing. One is you have to represent objects, and then you have to perform operations on them. Okay? And operations, we said, is basically algorithms. Okay? And now we have, this is going to take a lot more work to formalize, how do you mathematically define algorithms? Is there a simple description that can capture all possible algorithms, how to implement them, and so on? Okay. And does anyone know where the word algorithms comes from? The origins? Usually, no? Okay. So it comes from this 9th century mathematician called Al-Khwarizmi. Okay. And what did Al-Khwarizmi do? So it wasn't the first algorithm. We had algorithms that were being used since Euclid's days 2000 years ago, but still sometimes things stick. And he gave a procedure to solve quadratic equations. Okay. So apparently, people back in the day would have mathematical duels where they would give each other quadratic equations and you have to solve them. Okay. And of course, Al-Khwarizmi came along and killed the game by saying that, okay, here's a procedure. Now, if you follow it, anybody can solve it. You don't have to cleverly think about ways to solve it. Okay. And informally, what did he do? Said there is a sequence of simple steps. I mean, you can say, if I allow you to use operations, you can say my operation is to solve the problem, right? That's not very useful. You have to break it up into a sequence of simple operations. That's what an algorithm really is, right? You say, okay, manipulate these 2 bits, exchange these 2 numbers, and repeat, exchange these 2 numbers, and so on. Like that's like a sorting algorithm or whatever. Right? It's a sequence of simple operations to solve some problem. Okay. Is this a reasonable informal description of what we think of an algorithm to be? Seems reasonable, right? Okay. So let's work with this. But my claim is that even in this, there are 2 things which are ambiguous. Right? So what are they? Can you pinpoint? If somebody told me, this is my definition of an algorithm, it's a sequence of simple steps to solve some problem. What would you point out as vague here? Again, as I said, we don't want any ifs and buts. We want like full clarity in what we want. Yeah. Simple. What does it mean to be simple? Right? What we take for simple now is definitely not simple like 10 years ago. Right? Yeah. Exactly. The other question is, what does it even mean to say solve some problem? Okay. The rest is fine. Okay, but these 2 we have to define mathematically. Okay. And it turns out that we have to address now how to formalize this, and we'll see that, okay, maybe sometimes if we dig deep into just mathematically formalizing everything, we'll just get long list of symbols and not very useful. But here, it turns out that doing this formalization is actually very, very useful, both in making things very sound and also in building stuff. Okay, so we kind of get 2 birds with 1 stone, really. Out of these 2 things, which one do you think is easier to define precisely? Yeah? Solve some problem. Okay. So in fact, that is true. Defining what it means to solve some problem is much simpler than defining what it means to have simple steps. Okay. And this is a distinction that, if you've taken a programming languages class or software engineering class, you would have seen it specified. And it's this notion of specification. So the way we will capture solving some problem is just that we know objects are representable as binary strings. Okay, solving some problem just means that I have some function which takes a long sequence of zeros and ones and outputs a long sequence of zeros and ones. That's it. Okay, that's my entire specification of what's the problem that I'm trying to solve. Maybe you're trying to say that, okay, I have this video and I have to do some noise correction on it and blur the video or something. That's my input output behavior. But as we said, a video is just one long sequence of zeros and ones. And I want another long sequence of zeros and ones as the output. Okay, maybe my input is a database of images, and from that I have to pick out one particular image. Again, it's just mapping one long sequence of zeros and ones to another long sequence of zeros and ones. Right? So I can specify almost any computational task that I want in this way. Right? And I'm saying this is specification. We can't argue where this is coming from. That's what we're trying to do. Right? And for example, let's think of some common functions that we would like to compute. I already gave some examples. And one example that we discussed last lecture was multiplication. Right? So I'm writing it as n and n, but really you should think of it as 0, 1 star, 0, 1 star, 0, 1 star. Okay? And we can do this with impunity now because we know we already found out how to represent everything as binary strings, so we can push it under the box from now on. Okay? All right. And these two also we can view as really just a single string. So if you want to be really precise, the function that I'm trying to compute or what I'm trying to solve is this mul tilde, which takes a binary string as input, interprets that as two natural numbers, and outputs a 0, 1 sequence as output, which is to be interpreted as a number, which is to be the product of the two inputs. Okay, a lot of jargon, but the point is that you can represent everything as binary strings. Okay, so in some sense, combined with the representational stuff, we have solved how to specify what it means to solve some problem. Yeah. Right. So so basically in specification, there's only a single 0, 1 sequence, right? Whereas here we have two integers as input, right? So we would convert both of those to the binary, and then we would use our representation power to put them both into a single binary string, right? So the specification of multiplication would just be you take one long 0, 1 sequence, get the two integers out of it, and you're supposed to output the product of those two things. Okay, that's technically, very precisely speaking, that's what you should be talking about. Okay, yeah.
This is just, I think, going ahead of the just easy, but like we currently define what it means for like something to solve. But how would you verify like this is what it means for a problem to be solved?
No, that's up to our discretion in some sense, right? Maybe you say multiplication, but what you really mean is division. Then I can't really help you. But so somewhere someone has to specify this is the function that I'm trying to compute. Okay, and our abstraction is that we agree on what this function is, and now we have to figure out how to do this mapping. Okay. So there's this difference between, I think definitely you see it in software and so on, where you have a specification and then you have an implementation, right? This is the specification. Someone gave it to you, and now we have to figure out how to implement it, how to make it work on hardware and so on. Okay, we'll talk about that slowly. All right. Okay. So now we have to address the other challenge, which is going to take at least a few lectures now, and then it won't be a solution. Then you have to fix it again, and so on and so forth. how to define simple steps. Okay. We want the definition to be simple enough that it makes sense from an implementation standpoint or whatever else you might have in mind. But it should also be powerful enough that you can do good things with it, or it's useful for many things. Okay. So let's take a 5-minute break, and when we come back, we'll talk about this exactly. Okay. How do we define simple steps? Okay. We'll take a pretty pragmatic approach to this. We'll define simple steps by specifying some basic operations. Okay. And once we do this, this will lead us to our first computational model, which is that of Boolean circuits. Okay. You might have seen circuits in some other hardware classes, but here we're going to approach them from the perspective of a computational model. Okay. So we'll see it's a very concrete model that you can actually implement. Many early systems were based on that. And then we'll kind of revisit this model at the very end when we talk about quantum circuits. Okay. All right. So Boolean circuits are basically objects where the simple operations you perform are actually just 2 or 3, doesn't matter too much. Okay. And the simple operations are, the first one is AND operation. So the AND operation takes 2 bits as input, okay, and then outputs a single bit. So AND of A comma B is 1. If A equals B equals 1 is 0, else. Okay. The other simple operation is OR. And this is just OR of A comma B is 1. Let me say it this way. Okay, if A equals B equals 0, you get 0. Otherwise, you get a 1. Right? So these are the 2 operations. And then there's one more. We need 3. We can drop one. We at least need the third one for sure. And this is not. Not takes a single bit as the input and just flips it. Okay, if it's a 0, it outputs a 1. If it's a 1, it outputs a 0. Okay? And for brevity, we will say denote AND as and NOT is sometimes denoted as this fiddles, this tag, and so on. Okay. So these are 3 basic operations. And now let's see if we can use these 3 basic operations to build stuff. Okay. So for example, I'm going to specify a problem that I'm trying to solve. Okay, and this is the majority. Okay, meaning as I said, as long as I specify the function, you have to tell me how to compute or how to solve this using your simple steps, right? So majority is just 1 if a plus b plus c is at least 2 and is 0 else. Okay, so your inputs are 3 bits, which are denoted a, b, and c, and we have to output 0 or 1 depending on whether or not at least 2 of them are 1. Okay, and let's say I only give you the only simple operations that you are allowed are these ands, ors, and nots. How can you do it? Yeah.
Just like and A with
Let's see. So you said, okay, let me compute and of a with b, and then and of b with c, right? But you also need one more and. CA. Yeah. Okay, that's it. Now let me write it in a slightly painful way first. Okay. And then we'll simplify the notation. Okay, it's as defined, they are functions. They take 2 inputs, output a single output. Okay, so I can say this majority is and of a comma b, right? And then I compute and of b comma c. I compute the or of that, and then and of c comma a, and then or of this whole thing. Okay, so this is a painful way to just write. I compute the and of 2 things, or it with the and of the next 2 things, and so on. Okay, and if I use this even more logical, notation from logic, I can succinctly write it as just this. Okay, all 3 things are the same really. If I were to write it as a series of instructions, you'll say compute the and of a comma b, then compute and of b comma c, do the or of those 2 things, compute and of c comma a, compute the or of those 2 things. Okay, and you end. Yeah, all of these 3 things are the same. All right, so we have broken down how to solve the problem of computing majority by sequence of simple steps, where the simple steps are just and or. You are also allowed not, we did not use it, but that's all we did. Okay, so that's almost like we have an algorithm for computing majority on 3 bits. The next example is, we'll do a couple of examples and then we'll start talking about general principles. Okay, so the next thing that I'm interested in is the XOR, which is 1 if exactly 1 of a comma b is 1 and 0 else. Okay, so if you have 0 0, you have to output 0. If you have 1 comma 1, you have to output 0. But if you have 0 1 or 1 0, you have to output 1. All right, and typically you can also, it's helpful to sometimes represent these things as follows. You can say I have a, b, and then XOR of a comma b. Okay, this is called a truth table, where I write down the inputs and then the output next to it. So if it is 0 0, I have to output 0. Okay, this is called the truth table. So the terminology is from logic, but it just means you're writing down all possible values of the inputs and the desired output. Okay. Now you can ask the same question: how can I compute or write down a series of simple instructions to evaluate XOR? Yeah. Mm-hmm. Yes, exactly. Okay, this would work because you're exactly checking if exactly one of the two bits is 1. All right. And you can see there's a difference already between XOR and majority, in that for majority we did not need NOT, but for XOR we were using NOT. Right. If you think of, I can torture you by saying come up with a circuit or come up with a way to compute XOR with only ANDs and ORs, but there doesn't exist one. You actually need the NOT. Okay. All right. You can do the same thing again. Let's say I define XOR 3 now. The example 3 is XOR 3 which takes 3 bits as input and outputs a single bit. Okay. And what does it do? Again, the same thing pretty much is 1 if an odd number of ones, 0 else. Okay. So you have to output 1 if there is an odd number of ones in your inputs and 0 otherwise. So all zeros would be 0, all ones, for example, would be 1 now. Okay, once again, I can write down a truth table. Now I'll have 8 rows in it. I'm not going to do that. But let's say I ask you to write down a series of instructions for computing XOR when the only simple operations are ANDs, ORs, and NOTs. You might argue that, okay, XOR itself is a simple operation, but we're not allowed to change the simple operation, at least for the time being. We fix this series of simple operations that are allowed, the set of simple operations that are allowed, and then you have to come up with instructions on using them. You can't change the simple operations every time. Okay. So for XOR 3, how can I compute it only using ANDs, ORs, and NOTs? Any suggestions? Well, I'm going to save myself and all of you some trouble by kind of writing out things, very somewhat tedious calculations, and just observe that XORing 3 bits is basically XORing the first 2 bits and then XORing it with the 3rd bit. Okay, so it's really just this. Okay, and then I can apply this formula. As I said, as computer scientists, we always reduce one problem to another. We never solve new problems. Okay, so I'm going to reduce XOR 3 to XOR 2 by saying if I can solve XOR 2, which I already did, then I can solve XOR 3. Okay. All right. So these are simple examples, and we have a set of simple operations. And now let me define what it means to have a sequence of simple operations. As I said, we want a model where there is no ambiguity in what it means to say when you compute it. Okay. So the next step is to define what it means to have a series of simple steps. Again, as I said, this will lead us to Boolean circuits. But for that, for defining this formally, we need one more definition, which comes from graph theory. Okay, and this is the notion of directed acyclic graphs or DAGs. Okay, you might have seen it in CS32 or 33 or in 180. So what's the directed acyclic graph? Yeah, so it's basically a directed graph that has no directed cycles, right? So a directed graph that has no cycles. Okay, so for instance, this is a directed graph which does not have directed cycles, so it is a DAG. Okay. And I can also have another one. Sometimes it's not immediately clear from the picture that something is a DAG. So okay, so let's say I define okay. This is also a directed acyclic graph. There are cycles in it, but there is no directed cycle. There's no way to start from a vertex and follow the links along the arrows and then end up at the same point. Okay. All right. So that's one notion that we will need. And the other thing is more for sort of visualizing what we're going to define for Boolean circuits is we're going to draw these ands, ors, and nots. Okay, my drawing skills are pretty limited, so you'll see them morph into some postmodern versions of this pretty soon, but this is what they're supposed to look like. So an and operation or and gate will denote as follows. Okay, so it takes two inputs A and B, outputs and of A comma B, right? And this representation really comes from kind of how people built these things long time ago and even nowadays, where really think of these as sort of gates, physical devices, where there are two wires which take the input values A and B, and then the output carries the AND value of the two inputs. Okay. So really imagine you have this Lego block of AND gates. You have an infinite supply of these things. We have supply of OR things. You have supply of NOT. These are your sequence of simple operations. You have to glue these Lego things one after the other and build something. Okay. This arrow-shaped thing is OR. And then finally, a triangle with the circle at the end is meant to be NOT. Okay. All right. So why is this useful? It's useful to visualize something like this expression. Not that. Let's do this guy. Okay. So what am I saying? So with this way of representing things, we had the XOR, I can write it in the following way. So I have A coming in, I have B coming in, and then no, I think that's going to make it too messy. So let me do it this way actually. So I have this goes into an AND. This goes into an AND too. But okay. So here we're assuming in this representation, in this visualization, that the outputs can be duplicated. It's just a wire, think of it as electricity. It's just kind of glowing, I'm just copying it along the other wire. Okay. So the A comes in, kind of goes into two places. One is going straight to an AND, the other one is going to like a NOT gate, and same for B. Okay. And then now you put these two things together using an OR operation. Okay. And if I do all of this, I put my Lego blocks in this way, then what I get in the end is something that computes the XOR of A comma B, the 2 as XOR. Okay. Any questions? All right, now I can do the same thing for 3. No, I'm not going to let's see, how can I do that? Okay, I would get XOR 3 of A comma B comma C. Okay, so this would be the XOR sort of, the way to compute or follow a series of instructions to have the answer be XOR 3 of ABC. Okay. All right. So keep this picture in mind, and with this picture in mind, we can define the first formal model we're going to look at. And again, the definition will look very tedious and so on, but there's a point to it. We want to be very precise, and then the picture will make it very clear anyway. Okay. So what's a Boolean circuit now? So a Boolean circuit, which we will have 3 parameters for. An NMS Boolean circuit. Think of N as number of input bits. This is the number of output bits. And this is the size. Okay, size is meant to be the number of gates that you have. Right? So an NMS Boolean circuit is a DAG with n plus s vertices. So mathematically, a Boolean circuit is just a directed acyclic graph, okay, with n plus s vertices. And then we have to introduce some conventions on top of them, which is that exactly n of these vertices are labeled as okay, so you have n vertices of this DAG, which have special labels, which are x0, x1, xn minus 1. And the other s vertices are labeled as and or are not gates. Okay. So some vertices are labeled as inputs, basically x0 through xn minus 1, the n inputs, and some vertices are labeled as gates, operations. Okay. You can't have any directed acyclic graph. You have to have some constraints on them. For example, each AND gate has exactly 2 incoming edges. So each vertex which is labeled AND can only have, has to have exactly 2 incoming edges. And same thing for OR. Right? And then we need one more thing, which is each NOT gate has exactly 1 incoming edge. All right. So we almost specified everything, except we still have the outputs to specify. And we'll say m of the vertices are labeled as y0, y1, all the way up to ym minus 1. Okay. Makes sense. So you have just a graph with n plus s vertices. Some vertices are labeled ands and ors, and some are labeled as inputs. And in addition, some m of them are also labeled as this outputs y0, y1 through ym minus 1. So a vertex can have 2 labels. It can either be labeled as an input or a gate, and also as a output. Okay. All right. That's a lot of words for something that we can easily draw. And how can we draw a Boolean circuit now? So basically, we'll think of these, really think of this picture going forward. Okay. So you have a question? Okay. So we have a bunch of vertices, right? So which are x0, x1, all the way up to xn minus 1, right? And then you have these edges. For example, maybe this goes into a vertex labeled AND. So I'm just going to write it as an AND gate. Maybe this goes into a vertex which is labeled a NOT, which I'm just going to draw as a NOT gate, and so on. Maybe there is an OR gate here, which gets something else, and so on and so forth. Okay. And as we said, some of these are also labeled as y0. Maybe this is labeled y1. Okay. All right. So now we have a definition of what a Boolean circuit is. Right? What's the computational model that we are looking at? Okay. And the first thing to keep in mind, why this specific model? The reason really it started out, or why it gained prominence, was that we could actually implement it. Okay, starting from the very early computers, even to this day, pretty much everything is based on implementing these basic gates. So for example, people used vacuum tubes technology to implement ands and ors and nots. And of course, there's the whole semiconductor revolution, which showed how to use transistors to implement and, or, and not, and then how you can chain them. Okay. People have found ways to implement, physically realize ands and ors and nots using DNA sequences themselves. Basically, chemical reactions between specific snippets are used to simulate how and, or, and not work. Okay. You can also use it using other chemical reactions. It's actually fun to see some of these things on video. People have used crazy things like marbles. Right? But the most bizarre one, or at least to me, is something called fluidics. Okay? Where people use fluids to simulate ands and ors and nots. Okay? And let's see if I have that video here. Okay. Right? So and is basically if the two pipes go this this is a fluidic representation of and, or, and not. Okay. And now you can build a computer out of pipes and water. Why? I think there are some reasons that they give which I didn't buy, but it definitely looks fun. So you can do it. There is apparently a reason for this. Okay. Again, I find it very, very nice to say that, okay, give me a bunch of pipes and water and I can compute stuff for you. Okay. All right. And one of the reasons, why we are going to do what we're going to do is that it doesn't quite matter how we realize these things as long as we have the layering, the abstraction on top of it. Okay. You're using fluids, someone else is using transistors, someone else is using DNA sequences. You're all going to compute the same thing as long as you're just using Boolean circuits as your computational model. Okay. How you realize the simple operations should be material as long as you're putting the sequences together in the same way. All right, make sense? Okay, all right. So this, the fact that you could realize them physically definitely was very important in why they became so useful, right? But coming back to what we're doing, we defined what a Boolean circuit is, but we didn't actually specify what it does, what it computes, right? It's just a directed acyclic graph which has these weird names, labels, and so on and so forth. Okay. Now, once we have this model, we have to define what it means to compute with it. Okay. And that's what we're going to do next. And to do so, we have to review something else from graphs and particularly about directed acyclic graphs, which is this notion of topological sorting of DAGs. Okay. If I have a graph, which is a directed acyclic graph with vertices v and some edge set, then there is this really nice property that there is a layering of the graph, which you can think of as a way of numbering the vertices. Okay, such that the edges basically only go from left to right. Okay, meaning if I comma j is an edge, then the layer of I or the height of I should be less than the height of j. Okay, and a fundamental property of DAGs is directed acyclic graphs is that any DAG has such a way, such a labeling. Okay. So for example, we saw 2 examples of DAGs. Let's go to them. How can I label these things? Here at least it's a little bit easier. You can start by labeling this as 0, this as 1, 1, 2, 3, 3. Okay, the edges only are going from left to right in this labeling. The second one, maybe it's not as immediate from the diagram, but it just takes a few seconds. You can say this is 0. This is 1, 2, 3, 4. Okay. This is again a layering so that edges only go from a lower number to a higher number. Okay. All right. So now I can define how the DAG specifies an algorithm. Right? I have a Boolean circuit which is given by a DAG, and now I can tell you, okay, what are you supposed to do with this graph, with this representation? What are the sequence of steps that you're supposed to follow? It's basically what is intuitive, right? You would say I would first layer the vertices so that the edges only go from left to right. I would compute everything in one layer, and then compute, kind of carry the values forward in the next layer, and then the next layer, and so on. Okay? This is exactly why we need a DAG, because you can't have a cycle. Right? If you had a cycle, it's not a meaningful model. Right? So again, it's a lot of words, but we'll do this once or twice to be very precise. So we are given a Boolean circuit with n inputs, m outputs, and s gates. And I can define the following process, which is first, I layer the DAG via topological sort. Okay. And so that all variables are in layer 0. So let's assume that all the variables we put in layer 0. And now, if we have computed layers 0, 1 through k minus 1, we can now compute the values associated with layer k. Okay. So what do we do? Now, for each vertex in layer k, if it is an AND gate, Again, as I said, it's a fairly intuitive thing, but I'm going to spell it out in gory detail just to be very, very precise for once. Okay, we assign it the value of and of its incoming edges. Okay. If it is an OR gate, assign it the value of OR of its incoming edges. Okay. And without any surprises, if it is a NOT, then we assign it the value which is the negation. Okay. So just propagating the values from left to right based on the topological ordering. Right. And this now effectively defines a computer because we have a specific input output behavior. If the input is x0, x1 through xn minus 1, then the output is a binary string of length m, where I look at the values associated with the nodes which are labeled with y0, y1 up to ym minus 1 and just output them. Okay. All right, makes sense? So what we've done so far tells us that every Boolean circuit with n gates, n input variables and m output variables gives me a function. A way to transform a sequence of n bits into a sequence of m bits by a sequence of simple operations. Right? So we perform ANDs, ORs, and NOTs in whatever order specified by the DAG, and then we get some m values, and that is our circuit. It takes a sequence, outputs a sequence. Okay? And we can say a circuit C computes a function if okay. So remember we said there is a difference between implementation, or I said a while ago that there's a difference between specification and implementation, right? So the function, there is some function f that was given to us as a goal, right? That was a specification. Now we're claiming there's an implementation of it. We say a circuit C computes the function f if on every input what you get from following the circuit matches exactly with the specification f of x. Okay? So that's it. Now we have a computational model. We know what it means to compute something in this model. Give me any specific function f, which is like a specification, have an implementation by potential implementation by a circuit. Okay? Yeah?
Why do we have to go through the whole route of defining DAGs and everything? Why can't we just jump from saying okay, circuit is just we gave.
But how do you put them together? Right? So we had the 3 gates, which is good, but how do you put them together is important. Right? So in some sense, really, as I said, as we saw a little while ago, you can implement the gates in any way you want, right? But really what matters is the sequence of how you sequence it. In what order do you perform that, which is basically the DAG, right? Yeah?
How do you know, like like let's say you're given like an arbitrary function. How do you know like if a circuit exists that can like actually compute it?
That's a very important and good question, and we'll talk about that in the next lecture. Okay, it would have been, I mean, in some sense, maybe the answer is the fact that we are doing this means that it's worthwhile defining this model, and the reason is that you can actually do it for very interesting functions, have very, very good implementations, and that's those things really underlie much of modern computing, even to this day. Okay. Any other questions? So again, I don't want to do this in gory detail, but I can go back to, for example, this circuit and say, let me do this maybe just once. Okay, so if you think of the DAG representation of the circuit for XOR, it would be something like I have X0 and X1, and then I have this sequence of gates, and the last OR gate is basically labeled as Y0 as well. Okay? And when we come back in next lecture, what we'll do is study why AND or not. Was there something holy about them? Why did we pick them? And then also ask, okay, can I pick other things? And what power do we get out of it? Is this just like something that we could do because we could implement ANDs, ORs, and NOTs, and we were happy that with this specific set of simple operations? And see, there's a good reason, in this, there's a lot of robustness built into this model. Okay. And in any computational model, you should really look for some kind of flexibility. Okay. So it doesn't matter how we implement these simple operations, the model will still work fine. And as we'll see, it doesn't even matter the exact simple operations you allow. You can allow different things and still manage to do the same things. Okay, we'll address these things in next lecture on Monday. Okay, I'll see you all on Monday again.
Is the lecture notes for last lecture posted on?
Yeah, these are they're always available.
Okay.
I don't have to post them.
Oh, there. I don't think I can find last lectures.
So let's see. If you go here.
Oh, there are multiple sheets. Okay.
Yeah.
Also, I have a question about the Ling circuit. So you mentioned that the circuit only has N plus S nodes.
Sorry, N plus S nodes, yeah.
So what happened to the M output nodes? Do we not need to represent that?
So we're labeling some nodes multiple times. Like, a node can both be an input and also labeled as an output. It's just a convention. You could have said, I have to have new things which are labeled as ANDs or as inputs or outputs.
Yeah, how do you know which nodes are supposed to represent the outputs?
Oh, that has to be specified in the circuit. Like, in the DAG has to come with labels for which things are inputs, which things are outputs, which things are gates, and so on. So the specification of the circuit has to have everything, the graph and the labels.
Okay, cool. That makes sense. And also, layering just means a partial order.
It's a partial order which is consistent with the edges of the graph.
Okay, cool.
Right. So the consistency with the edges of the graph is, what's really important.
Like, what about problems where you don't necessarily know the solution to an input?
Right. I mean, give me an example.
Like, is there such a problem like where you know that there has to be one solution, but you don't?
Right. So I think, There are things where we don't know, but that's in the sense of, what problem to pick to solve in the first place.
Okay. But will we get into that later?
Done, thank you.
Yes. Yeah, so I think we have to assume that you have a specific problem that you're trying to solve.